Hi, this is Chris with Laughter on Water. I was watching Brady Haran's Numberphile video about Benford's Law, where Steve Mould was saying,
So what actually happens is that a third of the time, that's up here, right? A third of the time, the number you choose will start with a 1. And it will hardly ever start with a 9. So 9's kind of like down here, you know, tiny number. And then you get this brilliant curve that goes up like that.
and I thought, that was interesting, and what would it be like in octal or hexadecimal? About 5 minutes into exploring possibilities in Excel and 7 minutes into the presentation, Steve said,
and if you plug 1 into there, then it's log to base 10 of 2, and it ends up being about 30%. The beauty is that you can do it in any base. So this doesn't have to be base 10, it could be base 5, you know, base 16, whatever you want to do. And so you can apply Benford's law to different bases.
And I thought, well, binary only has one possibility, so it's going to be 1 100% of the time, not 30% of the time. A lot of dense information was conveyed, but I had to wonder, what's really going on here? The nice thing about science and maths in particular is that you can test your theories. I'm not good with brown paper and permanent marker, but I'm able to putter around in Excel, so I figured, why not test Benford's law? Of course, there are some fancy statistics packages out there that have been professionally vetted, including free and open source versions, but I'm familiar with Excel, and as this is more cooking than chemistry, maybe we can get away with it here. After all, we're just exploring the theory, not inventing something new. Let's test the theory. The first thing I need is data. There are plenty of resources for data we can use. I chose the U.S. Census Gazetteer population data for all census-designated places in the U.S., just under 30,000 points of data. After downloading the data, I used Excel to massage the information into something I could use. I created a column where I isolated the first digit. I also created a column with the number of figures because it's fun to find out where most people reside, big towns, little towns. Let's take a look. I want to be sure my data are correct, so once I've got all my formulae figured out, I like to do a few consistency checks. Is 8 the first digit in the population of New York? Yes, it is. Are there 7 digits in the population of New York? Yes, there are. Casually glancing down what I see above the fold, the numbers in columns D and E look reasonable. One thing I notice in Excel is that my numbers in column C are all aligned left, when the default alignment for numbers in Excel is to the right. That means the characters in column C are being evaluated as characters and not numbers, but since we're checking the verity of the character's existence rather than its actual value, that's okay. What about the bottom of my list? What's the smallest population? To my surprise, I found more than a few with 0 and single-digit populations. I can guess by the names that many of these are ghost towns, or towns that are, for lack of a better word, dying. I might need the total number of data points to check consistency of data, so I've marked that here for future reference. Now that I'm comfortable that I have the first digit for each population, let's graph how many times each digit appears. Of course, for this set, we have some 0 populations, so I've included 0 in our data, because the only time 0 appears as a leading figure is when it's the only figure, 0. I wikied Benford's law to look closer. It's also called the first digit law and should not be confused with another more humorous Benford's law we won't discuss here. When I scroll down to view the standard example of PD, I see the percentages look fairly similar to what happens with the U.S. population. Using Excel, I've been able to verify Benford's law. From multiple natural numbers spanning multiple orders of magnitude, 1 appears very often, so Excel seems to be giving reasonable results for this set of data. Let's try another data set, daily rainfall for days it rained in Tampa, Florida in tenths of a millimeter from 1936 to 2010. I got this data from the NOAA Weather Service. Whoa, that looks all choppy. The margin between orders of magnitude may make these data too similar to adhere to Benford's law. Of course, we could mix this data into other data and once again achieve a reasonable curve approximating the first digit law. One of my favorite numbers is the Fibonacci series. Let's see if we can apply Benford's law to that. If I graph 10 consecutive numbers from the sequence, regardless of where I start in the sequence, I always get a pie chart that looks like this, whether I start with 1, 2,584, or a much larger number. This graphs in the opposite direction and isn't even about Benford's law, but it's a fun property of the Fibonacci sequence. Of course, we want to take the first digit for as many of the numbers from the Fibonacci sequence as we can before Excel breaks. Excel starts to break when we start seeing lots of zeros at the end of each number. It's approximating our numbers to 15 figures and giving up after that. But since we're only interested in the first digit anyway, I'll use these numbers and see how far we can go before Excel totally breaks, which in this case is at the 1478th iteration of the sequence. I'll take what we can get. Let's graph it. The first digit graph for the first 1477 iterations of this series looks exactly like our US population data, suggesting that the Fibonacci series of numbers adheres to Benford's law. But what about creating a set of random numbers in Excel? Actually, I already know that Excel has been criticized for its poor statistical abilities, but maybe we can get around that by creating our own random number generator. First, I need to test the limits of what Excel can do for me. It's a bit like frying an egg to test a new frying pan. Excel has a couple of random number generators, rand and rand between, but both generate a fairly consistent number of digits. Even though I've selected rand between for a random distribution of numbers between 1 and a billion minus 1, most of the numbers contain between 9 and 8 digits. The difference in order of magnitude is insufficient for our needs. However, we can add a little chaos to the system by magnifying a billion minus 1 by a random percentage, then round to 0 decimal places to get a very wide variety of random numbers with a wide order of magnitude between them. Looking at this column, I'm satisfied with the variety of difference in magnitude. I want to play with other number bases, so I convert my decimal numbers to various other bases. The first thing I notice is that octal, or base 8, is messed up. It keeps breaking in the octal test column. What's that about? Most of the numbers look fine, but randomly, some break the conversion function. After a little trial and error, I found out that the functions for octal conversion don't work when the number is larger than octal 4 billion. I explored the limits of the octal and hexadecimal conversion functions to see at least what magnitude it takes to break Excel. Octal conversions break somewhere between 100 million and a billion in base 10. Hexadecimal breaks several orders of magnitude above that. And a base 36 conversion function I found online breaks somewhere in between. All of them break above the size of any random city population, so a random function that stays below 10 million in base 10 should be adequate for generating various curves in any base I choose. Getting back to random number generation, I decided to create numbers that look similar to our US city populations. I used an arbitrary formula shown here where variable ny is the 2010 population of New York City. By visual confirmation, I see plenty of magnitude change and no cities over 10 million. Let's apply this to a very large number of randomly generated pseudo-city populations, then create octal, hex, and 36 base equivalents and their first-digit homologs. Looking at the decimal conversion, the pie chart for our random numbers is identical to the one for US populations. Magnitude also falls under a curve. The octal pi shows 1 coming up 33% of the time. The hex pi has 1 coming up 25% of the time. Base 36 shows 1 as our first digit at just under 1/5 of the time. Because there are more characters in larger bases, 1 doesn't show up as often as it does in base 10. But what are the extremes? We can step behind the scenes and plot Benford's law using its formula to derive the ideal PD for each character for any number base. Let's start with binary and plug in the numbers. Notice that 0 breaks the formula. Ternary numbers start with 1 63% of the time. In quinary, 1 shows up 43% of the time. As the number base increases, PD decreases. The formula shows identical statistics when comparing the US population to randomly generated populations in base 10. At this point, we start to glimpse what happens at the extremes. For base whatever in the leftmost column, 1 shows up with decreasing frequency approaching 0. Because 100% is the highest we can go, only binary can achieve this, but here's some weirdness in our calculations. When I look at base whatever, starting with binary, 1 shows up 100% of the time as we expect. So how can 2 show up 59% of the time? In ternary, for example, 63% for 1 and 37% for 2 make up 100% of our possible character appearances. So how can 3, 4, and 5 show percentages when they're not even in the character set? What is up with that? Remember these numbers, we'll come back to them. Let's show what happens in ternary and assume a similar approach can be taken in all other bases. Ternary 3 is written 1, 0, ternary 4 is written 1, 1, and of course ternary 5 is written 1, 2. Given our random populations sample, when we convert to base 3 and collect the first 2 digits instead of the first 1, we can count just the number of times each first 2 digits appear in our base 3 random population. So we count the number of times 10, 11, and 12 show up as our first 2 characters. When we divide these totals by the total number of random populations, we get percentages that almost exactly corroborate the perfect curve from our base whatever graph. Cool! In any number base, the PD for 1 has the highest frequency in any set of natural numbers, given a wide enough range of magnitude. But 1 doesn't always show up about 30% of the time. That only happens in base 10. As number base increases, PD for number 1 decreases. No, I'm not finished yet. Remember those other pie charts of the Fibonacci series and how, regardless of where we started, we got the same pattern in the pie? A similar sort of holographic mapping happens with data in Benford's law. We know what the pie looks like for the whole set of U.S. populations, but when I take any half of those populations, or a third, or a fifth, or even a tenth, as long as I still have a reasonable amount of data, any random portion of the same data will also comply with Benford's law and therefore graph similarly. So when I came across the rainfall data for Tampa, Florida, I was curious about what would happen if I graphed half of that data. Indeed, its graphs look nearly identical to each other in how they differ from Benford's curve or pie. I tried the same thing with Orlando, Florida rain data and still got a similar result. It seems too uniform to be coincidence, so I also graphed data from Kent, Washington on the other side of the country. It shows nearly identical variance from Benford's curve. It doesn't seem to matter which rain data I pick in the U.S. The structure of the graph is not exactly Benford's law, but differs coherently in such a way that it seems to act like a fingerprint of the kind of data I might be interested in. I wondered if other data might also have unique fingerprints, so I tried land in square meters in all U.S. county subdivisions and got a different fingerprint. Likewise, Puma data for land in square meters gives its own distinct fingerprint. In the same way that Steve suggested Benford's law could be used for forensic accounting, I wonder whether these aberrations of Benford's law could be used forensically as fingerprints to determine what kind of data a random set of numbers might be. For instance, I could create a random set of pseudo-rainfall data for Tampa, Florida. Except when I do this, I get numbers that adhere more closely to the standard Benford curve than the fingerprint I see for real rainfall data, suggesting I could not use strictly random numbers as generated by this simple Excel function to emulate rainfall data. Anytime we explore to discover answers, more often than not, we uncover as many, if not more, questions in the process. For me, this avenue of inquiry has provided a lot of questions. Here are some examples. 1. Could I develop a formula that would spew data that emulate U.S. rainfall data when subjected to Benford's law? 2. What happens when we apply Benford's law not just to the leading digit, but for the nth digit or the last digit? 3. Perhaps U.S. county subdivision land areas don't fit the curve because the way land is parceled out isn't entirely random. In other words, legislation and history may have played a role in why this curve varies from Benford's. Similarly, when accounting numbers don't fit the curve, Benford's law can be applied forensically to discern whether someone has been cheating on their taxes. If this assumption is correct, the implication is that if numbers don't fit Benford's law when they should, perhaps those numbers are not entirely random. What does this imply about fairly unimpeachable sources of natural data like the U.S. rainfall data? 4. What other data might exhibit distinct aberrations of Benford's law and how might they be made useful? Using tools at hand, anyone can explore laws like Benford's. What are you exploring? Please write comments and subscribe. This is Chris with Laughter on Water. Thanks for watching.